Good morning, everyone. Last Thursday we had a test, right? Okay, so this is the first time I tried. I got a little scanner with the foot control. So your for this class, they say don't hand back the exams because it does have a multiple choice part, and those are difficult to create because of you can scramble the order, but making good distractors is almost a full-time job. So what I did is I scanned in what your answers were, but you don't have the multiple choice questions to review and such. Those I do have available after when we can do those during office hours, which the best one for this class would be right after class. What I'm going to ask is today, if we could wait maybe till Thursday to review any of the multiple choice. And it's not because of you, it's because my mind is just fuzzy right now. So I gave exams in my 210 class as well. So but if you really need to see them, we could talk about them. But what I'd like to do kind of this week is start focusing on the next section, which is going to be exponential functions today. Well, let me go over this. So we're now on to Module 3, exponential and logarithmic functions. I did a little screenshot from the syllabus of what's going forward from this point to the next test. So we've got exponential functions today. We've got logarithmic functions on Thursday. So this week we're doing both. And regardless of how you did on the first exams, oftentimes students will find this next section easier in the sense that the content is more compact. And you may have either done exponentials and logarithms before, so it might be easier because of that. If you haven't, the thing is the algebra we covered, while a few sections, there's a lot of stuff that it's coming from, right? This stuff, it's more compact. So typically students will do better on this section. We're going to get into trigonometry, and it's also the same thing. It's an area where, well, let me give you an experience. I had a student from when I was at Oregon State. He was from Mongolia. He was in my algebra class and was really struggling because English was not his first language, and math was not his love of his life. So let's put it that way. And he came to me and says, I'm not going to get through your algebra class. He says, but I looked, because the book we had both algebra and trig. He says, I can memorize my way through the trig class. Will you let me drop this class and take the trig class next semester? I says, well, typically trig has a prerequisite of algebra. I said, there is some algebra in there, but I says, if you feel you can do it, I will do it, because all he needed, he wasn't going into engineering, he just needed a math class. So I let him do it, and I saw as he worked through that class, he had flashcards this thick, and he memorized all the trig stuff. He got an A on it, which I would not have, I wouldn't have probably been able, because against the traditional way we say you have to have your algebra's in there, but so trig is a different sort of thing, which may be good for you or bad for you. So if you've done really well in algebra, it might be that you're going to struggle in the trig, or maybe not. It's hard to tell. But hang in there. Again, whichever you did on the exams, keep moving forward. One thing I'm going to do, because I noticed in the multiple choice, I was thinking of this as I was grading, but I was just trying to get through it, and I spent somewhere between 8 and 10 hours on the grading process. Is on some of those multiple choice, there's multiple ones, and half of it's right, half of it's wrong. And so if you chose one of those ones that's half right but half wrong, what I'm going to do is I'm going to go back and I'm going to figure out, I feel you should get half points. Okay, so there's some where there's like three answers that two of the answers will get half points, one gets the full points because it was completely correct, and then there's a few of them that were completely wrong, so obviously you shouldn't get partial credit for those. But I will go through the list, and I think there's maybe at least 3 of the questions, maybe 4, where I can do that. I can, based on your answer. What I'm going to ask for you to, I'll put out an announcement. I'll ask for you to review yours and for you to tell me I should get half credit on this one, this one, this one, or whatever. And then I will go back and add those points in. Of course, it's all in the grade book, because I uploaded your scanned copy so I could take a quick look. But if you'll just, if we'll do it that way, okay, so that can get you somewhere between 5, 7, maybe even up to 10 points, depending if I've had 4 partial credit. And again, I'm not sure. I know there's at least one. I think there's 3, at least that there's 2 good other candidates where at least one of the questions would be half points. And I think that'll sound, that's the fairest way to do this. On the ones you provided the answers, the written, you have copies of those. I mean, you have a scan of those. If you feel like you should get more points on one than the other, I tried to be as, on the partial credit if you didn't get everything. But I'd be happy to talk through those too. You could, So, but again, it's the first thing, and a lot of times taking the first test, you'll see the next test will be somewhat similar as far as multiple choice and stuff, and we'll just keep moving through. I also, on the homework for the previous one, not that I want you to focus on it, but the due dates didn't change, but there's a secondary due date that it will still be accepted, and I moved that to the end of the course. So if you want to, because as we get close to the final is comprehensive, so it's worthwhile to go back and review, and those should sort of update. The other thing is I mentioned that if you had 70% or above, you'd get the full points. I processed that, but I'm not sure if those points stick or whether Pearson comes back and updates. I haven't even checked at that, but I'll take a look. Question here.
Are we expected to memorize the unit circle?
You're expected to know how to construct it. Let me put it that way. I wouldn't memorize it. I can't memorize it, but I'm going to show you a way. If you can count 1, 2, 3, you can recreate the unit circle. We will practice it. I've got a video. I'll share that with you, but it's just the pattern and then going around. And as you construct it, you'll be able to reconstruct a unit circle in less than a minute. Once you practice it a few times, I will provide you a template of a unit circle that's blank, so then it makes it a little easier to just sort of fill in the numbers in 1, 2, 3, 1, 2, 3, square roots. So it's I'll show you a method that if you just sort of, it's a process you can remember. Because here's the thing, is you're going to take, most of you are probably going on to the 265 calculus, or maybe you're going on to a version of calculus that has trigonometry in it, and in those courses they're going to expect you to memorize or know what they are. I can't, but I can at least do the first quadrant real quick, and then I could figure positives and negatives. So there's really, there's 3 things that you really need to sort of remember, and we'll get you through that. Okay, so I have taught the 265. If you take it again, I just like here, I record all my lectures, so the course is the same. I got exam reviews on my YouTube channel, so when you take that one, you may want, I've had my previous students who took this course come, I say, here, just watch these videos. But that's one of the things is that. Okay, we ready for exponentials? Okay. So the nice thing is now we're down to about 2 lessons per week, which means we don't, before with 3, we were really kind of having to do 2 in one day, or 1.5, and then carrying it over. So I think the pacing also will be a little nicer for this section. We can do 1 a day, take a break. We'll do Thursday, we will do logarithms and properties, so next week. So it's just, and during fall break, we only meet once, so we've only got 1. So it's really just one lesson per class period, and then we'll get into the review. Okay. And I realized again, because I spent so much time over the weekend, I haven't really set this up. In fact, it was, I think, early this morning that I I did make available module 3, and I've got the exponential function one set up. I haven't gone further than that, so this is what I added this morning. I've got the slide deck. We'll use that to talk about exponential functions. I've got a video from my online course. Again, it's basically me going through that PowerPoint or that slide deck. So that's, and it's a little more polished. I am recording this, and I'll post it here as well. So it's not as polished, but sometimes it's better because it's going to include any questions that you ask. So exponential functions. So what is an exponential function? What does an exponent do? Oops, let's see. Let's come back here. What does it mean, 3 to the 4th power? How would I calculate 3 to the 4th power? What do I do with those? Is that 3 times 4? Okay, it's repeated multiplication. Good. So that's 3 times 3 times 3 times 3. Is it the same thing as 4 to the 3rd? No, because that's 4 times 4 times 4. So each part, there's a base. So we're getting a little thing here. We call this part the base, and that's what is getting multiplied. And then we have, let's change colors here. We have the exponent or the power. We use multiple words for that, but that's the number of times of multiplication, the number of times that we're going to multiply. And for an exponential function, what we're going to do is we're going to have a base, like 5, and the exponent's going to be a variable. That's the defining part. The variable is now up in an exponent. And we're going to see that's why to be able to actually solve these, we're going to need logarithms because it's up there sort of where we can't touch it. It's like basketball players holding it up here, and they're 7 foot and I'm only 5'10", and I can't reach it, you know. So we can't reach that exponent at this point. But if that's an x and exponential functions are repeated multiplication, what does it mean to like have 5 to the, because x could be any number, right? It could be a decimal. Does that mean I multiply 5 half a time? Yeah, sort of, but so all the x could be, and it can be negative. So we're going to see that x now, the difficulty with exponential functions is we quickly, whenever we have a decimal, we lose the feeling of what's really going on. We know that if it's an integer value, 5 squared, 5 times 5, that's 25. But how many of you memorized your exponential tables like up to the 5th power? You know, that 5 to the 5th? No. Maybe squares. We're doing okay with squares, maybe up to 9, maybe up to 10. 10 squared is 100. Okay, I'll give you that one. Maybe some of you got 12 squared. That's 144. I only got that when I was a teacher. I never had that as a student. But certainly I don't know what 13 squared is. Maybe I do. 169. Yeah, so there's a few. 17 squared, you know, we don't know those things. And certainly if you do, that's good, but you're probably not really keen on what 13 to the 4th power is, or 13 to the 5th power. So what we end up with is it's less intuitive than when we were doing like algebra of just multiplication, addition, and subtraction. Okay, so because we haven't memorized all these things, and we get to these things, and then, you know, let alone what is 5 to the 5.5 power. you know. But what we're going to do is that's where we're going to really need our graphing calculator. We'll explore it these ways. Okay. So actually, I had a whole thing on that. So we have some base a, and we define a. It has to be the base has to be greater than 0. And the reason is if you put if a were negative number, let's say even -1 is probably the easiest, but what happens, say it's -2, if that was our base, if we do it to the first power, what's -2 to the first power? -2. But what's -2 to the second power? It's a +2. Oh wait, +4. See, I was just focusing on the sign. It's +4. What happens is that if we were to allow that, it's a function that kind of jumps back and forth from being positive to negative, and it's not a well-defined function. It's just kind of it's not continuous for the first thing. I don't know what it would look like. We try it on your calculator, but it's a mess. So we say no, a has to be greater than 0. The other thing is we say a is not equal to 1, and why would that be? Well, what's 1 squared? It's 1. What's 1 to the 3.75 power? That's 1. What's 1 to the millionth power? That's 1. It's 1 times 1 times 1. So it's kind of, it's not exponential because it's not that it's not a function. It's a horizontal function. It's always 1. Okay, but we don't define that. But it's also a boundary point. If you can remember, 1 to the x is sort of that boundary where we have a constant function. So it graphs out as a horizontal line. What would happen? Constant. What would happen if the base was less than 1? So 1 is kind of the dividing line. Or what would happen if we had a bigger than 1? 5 to the x, right? We keep multiplying by 5, by 5, by 5. We get bigger and bigger. .5 is a half. If you keep multiplying by a half, right, you get a half. 1/4. Square that times 2, you get 1/8. 1/16. We get smaller and smaller, right? So it's going to be, and we'll see basically when we graph these. So x to the 0.5 kind of looks like this, where it's going to decrease. X to the 5th would look like this. It's going to increase. And 1 to the x, or did I say 5? Yeah, it's just a horizontal at 1. So those are what the graphs will look like. And again, for understanding this section, we really need to look at the graphs, because we're never going to get there where we can memorize the exponential table. It's just so all over there, but we can see how each one works. Okay, so the limitations on the base, let's take a look at what they look like. And again, I like to use Desmos as an exploration tool because it's usually fast and easy. So if I have a function, and we'll do that 0.5 raised to the x power, and right away it sees, as x gets bigger, that's really like the same thing, right, as 1/2 to the x power. That's the same function. Okay, so it's a decreasing one. If we have a number bigger than 1, call it g of x, 3, then we see that's something that as we go through is going to increase, right? So it's an increasing function. We can trace along here and see various values. One thing we notice is what happens when x is 0. When x is 0, what is the y value? It's 1 for both of these. And you'll see that's sort of consistent. If we have because what is anything to the 0 power? Yeah, 27 to the 0 power equals 1. Of course, the only exception is 0. 0 to the 0 power is undefined. It's indeterminate form, because you either define it as 1 or anyway, it has problems. But everything else, we say anything to the 0 power is going to be 1, so that's going to be something you're going to see. The y-intercept of all just pure exponential functions is always going to be y equals 1. Okay, so we see it going through there. So there's something we pick up. And again, if we try to graph, let's see, while we're here, let me get rid of this one. We don't really need it. If we try to graph y equals 1 to the x power, we see we just get a constant. So it's not defined as an exponential because it's just a constant function, but just remember it as the dividing line between increasing and decreasing functions, the basis anything else. And sort of let's see what would happen if we try this. Y equals, let's go with this -2 raised to the x power. And I don't know, it might blow up my computer. And what you see is you see all these little points here. And maybe, or is that just, no, those are actually points. So it can graph a few of these, but it's not a well-defined function. So that's why we don't use negative bases. I didn't even know what was going to happen, so I'm glad I tried. Sometimes just try something. Okay, is it all making sense so far? Okay. And remember, today we don't get to the place where we're really going to be able to solve these, except so part of it is we wanting to just understand what they are. So part of it is what's the domain of an exponential function. Well, the x's can be anything from negative infinity to positive infinity, so the domain is always negative infinity to positive infinity. But as we see this on a standard function, the range, now notice 0 is not included. You can't actually get it equal to 0, but it gets closer and closer. So that's our horizontal asymptote is 0. Okay, so our range is always 0 going up to infinity. We talked about this. The y-intercept is always 0, 1, because when the exponent is 0, whatever the base is, anything to the 0 equals 1. So these are some features that are going to be true of every single one. So that gives us a horizontal asymptote, y equals 0. In this case, the graph is increasing whenever the base is bigger than 1. Okay. The reciprocal of base 3. So what would be the reciprocal of base 3? Well, that would be 1/3 to the x, and that we've actually already graphed, or something similar, right? Let's see if I go back here. Maybe I'll change this to the 1/3 power, and they look like one was reflected over the y-axis, doesn't it? They look like they're matched up. And why would that be? Let's think about this. Well, what is 3? Let's think of that x. What if it was 3 to the -1? What's that going to be equal to? 1/3 to the 1. So we see that these two functions are related to each other. From the negative side, it's just, and then if I had 1/3 to the -1, what would I get? The reciprocal, 3. So in fact, the negative sides is really a reflection of the positive sides. Yes, sir.
When you had 0.5 up there, how come that didn't look like it was reflecting over like the -2? Like it should.
0.5. It should. Now this one, let's clear this up a little bit. So let me get rid of this one. Let me change this to 1/2, and then this to the second. So now they're a mirror image of each other. Does that make sense?
Yeah.
Okay. Yeah, I had some, but yeah. When I had that negative 1/2, that was a weird one. That's okay. So we can kind of see a relationship between 3 to the x and 1/3 to the x. One gives us an increasing function, one gives us a decreasing. And so we see, yes, it's coming the other way. The domains are still the same, infinity to infinity, negative infinity to infinity. So even the reciprocal function, we see that the range is the same. We see the y-intercept is the same. We see the horizontal asymptote's the same. The one thing we see is that it's a decreasing function instead of an increasing. Okay, so it's going down from left to right. And we can call it a transformation, right? Well, because we talked a little bit about transformations in the last part. We kind of bring that into this. That's a topic that's going to be consistent throughout. Even when we get to trig, we talk about transformations. So we get the standard function. We move them left, we move it right, we up and down, we stretch them, we do those kind of things. So that's another thing that you'll want to go back and review. So if we wanted to vertically translate something with a base of 3, what would we do? Let's think through this. So if I had 3 to the x power, how do I move it up? Plus something, right? Plus, we'll call it plus v for vertical. If v was negative, what would it do? Move it down, okay? And again, you can play with it. See that works. So we'll graph y equals 3 raised to the x, and then we'll put plus v, and then when you put in a new variable, it lets you put in a slider. Notice if v is 0, we haven't done it, but if it's anything positive, it moves it up. This is what I like about the sliders. You can actually see it moving, right? And if I go down and it's negative, it drops it down. So that, again, we're adding something outside the function. We move it up or down. While we're here, I know where we're going. How would we move it left or right? We would add plus h, but where would we add h for horizontal? Where would we add the h? Inside the function, right. Where is inside an exponential function? The exponent. Very good. So these are the kind of things we need to pick up. The inside of an exponential is that exponent. So we want to come up here. And again, just to ensure order of operations, I put a parentheses around it, and I'm going to put plus h. And again, that'll give me a slider. And I'm going to click on this. It started my slider out at 1, and notice I'm kind of over there. So let's go to 0. I'm adding, so this is our standard. And if h goes positive, what's happening to it's sliding in what direction? The negative direction. So remember, inside operates the opposite of what we think it's going to do. And if it's negative, it actually goes in the positive direction. So we can see we can control positive left and right translations, right? Up and down translations. So we start to see these functions building off of just the standard 3 to the x. So we okay so far? Is this making sense? Okay, so you see the other part is as we go forward, you start to build on things we did before, and they make even more sense because we see them in a different setting. Okay, so yeah, answers here. We added 2, it moved up 2. And so there's all that stuff. And again, that'll also change the range, right? Because the range was going down to, but if we move everything up 2 instead of going to 0, it's now going to get close to 2. The y-intercept moved up 2. It was 0, 1, it's now going to be 0, 3. So as we make these transformations, everything else moves as well. Okay. So if we can, again, part of it is just think of what is 3 to the x or whatever the base is, and then we can apply some. And we just, see, I knew we were going there, so I went ahead and did it all at once. Horizontal translation, right, is going to be up here. We're going to add or subtract h, and I just do add h, and then if I want to subtract, I just make h negative, right? And if negative h's moves it to the right, positive h's actually move it. Positive h's move it to the left, and negatives move it to the right. Okay. How about reflections? How do we do reflections with a function? What is the one little thing that causes a reflection? Negative signs. Good. So if we put a negative on the outside, that's going to change, think of it, it's going to change all the y values. So negative y's become positive y's, so it's going to reflect over the x. So it's kind of backwards. So we could put a negative on the outside here, which again is outside the function. This is going to reflect over x. And then if we put a negative on the inside, which is up here, what's that going to do? What other axis do we have? The y-axis. And we've already really sort of talked about this 3 to the negative x, thinking of it as 3 to the x versus 1/3 to the x, because that's really what the negative exponent does. It gives us a reciprocal. Okay. And again, we could explore it, but we kind of already done that. Well, let's do it with a let's just do 3 to the x. And we see that flipped it over the x-axis. And then y equals 3 to the negative x. And that flipped it over the y-axis. Okay. A number that comes up a lot, especially if you're in like biology, depending upon what science you're in, is we use something called the base number e. So we're going to have this. The first thing is, if you haven't been introduced to e before, you oftentimes think it's a variable because it's a letter, but it is a number that is similar to pi is for circles, right? Pi is 3.14 with non-repeating, non-terminating decimals. It keeps, get out there. E is a similar number. It's a naturally occurring number, and that's why I say in biology it occurs sort of naturally. The shells of a nautilus and stuff. And it's approximately 2.718 something. I remember that's 3 decimal places. It's close to 3, so if you use 3, it gives a good estimate, but it's not exactly 3. It's, so it's just a naturally occurring number. And so instead of writing out all these decimal places, we just use e, and it's stored in the calculator to give us more accurate answers. The thing you find with the exponential is how quickly do exponential functions grow? Exponentially, yes, that's good. Which is fast or slow? Very fast. And we'll see, so actually exponentials are the fastest growing functions we're going to consider. So they are the fastest ones in town, which make their sort of their inverse, the logarithm, the slowest growing function. So they give us both of those. So the thing is since it grows so fast, a little change in that base from 3 to 2.7 makes a big difference because we're multiplying and stuff. Okay. So, but on your calculator, there's a key for the E button, and usually it has e to the x because E really always needs an exponent. Let me go to here, and usually they have it somewhere like in the functions key. Let's see if we got. Yeah, you'll see the logs. Let's see, where do they have the? They don't have it here. If we just put the letter E here, it's going to, and you'll see 2.7182, so it's this long, you can kind of see it. But usually E is, I mean, we could have just E, it's right now to the first power, right? But since we're doing exponentials, we typically, where's the exponent key? Do it this way, to the x power. And as I said, it's very similar to 3 to the x power. They're very close, but 3 to the x power will increase faster because they are a little different, but just think of e is close to 3, but it's somewhere between 3 and 2. Actually, if we put 2 to the x in here, you see it kind of lives between it. It's closer to 3 to the x because it's 2.7. But that's how exponentials work as well. That base is very important. Okay, so far so good. So just e is that natural number. And we use it through the point. So two things is we're going to look at how to solve. Well, first how to evaluate and then how to solve. So here's a problem. A lot of things that are exponential processes are things that happen over time. Cooling or heating is typically will happen exponentially. Any of you cooks, you kind of, you're sitting, you watch and watch. It looks like it's never going to boil, and then all of a sudden it boils, right? So when it starts boiling, it takes off. So how do we evaluate? We want to find, so we've got a function that gives us a temperature based on the time it's been cooling. We want to find after 15 minutes, how would we evaluate this? One way, we put the 15 in for x, do the calculations, you'll get your value. What I'm going to encourage you to do, let me pull up my calculator here. I'll use my TI calculator just so you get used to using your handheld. Hopefully it lets me go in without having to sign in too much. Let's see, where are we? We go till 10:15, so we got time. We should find that we're ending a little early each day, maybe 15, 20 minutes or so. Get this stuff out. So we're going to actually come back here. There we go. So we actually just enter it in. So there's this negative key. So on a TI-84, you've got to be careful. I've got some of my brief calc class will still use this, but this is for subtraction. This is the negative key. So negative 8 plus 24. And then your E key is right, there's this ln, which is a natural logarithm. We'll talk about that on Thursday. But e to the x is a blue, so we have to go second e to the x. There, we got it. And notice it'll give us that exponent. It's waiting for us to put that exponent, and what we want for that exponent is negative, and that's this key, 0.028, and then x, the variable. They use t, the calculator will use, okay, so they're using x. And then just to evaluate it at 15, what we can do is we can go to the table. And again, I'll go to table set. Your table, when we're doing this, you should have your table have your table changing by 1, have it on auto, and then when we go to the table, here's all the x values and the y values they produce. So we come down to 15, and there it's going to be 7.7 Celsius or whatever, you know, that's our temperature. So after 15 minutes, it's cooled down to 7.769 or 7.8. Celsius. So it's a soda, we're getting it colder. What is the significance of 0 degrees Celsius? Freezing. So it would turn to ice at that point. So, well, you probably don't want it down to 0, but 7, that might be good. Okay. The thing is that's good about going with using your graphing calculators. We've got this. The other thing we can do is we can go to the graph and we can kind of see it here too. And if you go to trace, you can actually trace along here. Trace is a little bit harder. We could get x equal to 15. There we go. And we get the same value, but here's another way we see the whole process of how it's going. You know, we see if we leave it in there according to this formula, at least it's going to get colder and colder and colder. Okay, so another powerful way to examine the functions. And that was it. Now, I haven't unfortunately, looked ahead to the homework, but let's say, let me bring this back. Let's say I would like to know how long am I going to need to wait until it gets down to 3 degrees Celsius, because that's when I want it really cold. How would I figure out how long it's going to take to get to 3 degrees Celsius? That's a solved problem, right? So let me come back here. So what if we, instead of evaluating, we were asked to solve this, when is this going to be equal to 3, right? How do I do that with a graphing calculator? I graph the first part, right, which we've already got. What do I graph for the second part? This also is a function. What is the function 3? Y equals 3. It's going to be a horizontal line, and so you'll get hopefully comfortable with this. We can solve any equation using a graphing calculator if we graph one function and then we graph the answer they're asking us to get, right? So we'll put y2, we'll put 3, y equals 3. It's going to be a horizontal line. and then where they intersect is what? That's our answer, right? And so the way we can get the intersection is we go second calc, the trace key, and notice there's a function number 5 for intersect. And the reason I show you this with a TI calculator, it's a little cumbersome. They ask which is your first curve. Notice it's little spider guys flashing on this one. All I have to do is hit enter and say, yeah, that's my first curve. It jumps to the second curve. Yeah, that's my second curve. It asks for a guess. I say, paid $140 for you. You guess. I just hit enter, and it will find the point of intersection. Now, sometimes you need to use that guess if there were more than one intersection. You have to be. It'll get whichever intersection it's closest to. Okay, but this is a way. If you've got two functions, it doesn't have to be one. You can graph them both, and the intersection points is where the solution lies. Okay, so we do that intersect. Some of the other, the Casio calculators a lot of times will just show you what that intersection is, which is nice. Desmos, if you use it, it shows the point of intersection. You don't have to do much. You maybe click on it. But this one you have to actually kind of jump. So if I had 3 different graphs in here and I want to find the intersection between 2 of them, I have to be sure I'm choosing the right 2. But if you've only got 2 graphs, you just kind of go intersect, enter, enter, enter 3 times, and you'll get your intersection. So it's going to take me 27 minutes, 27.86, almost 28 minutes, right? And it'll be down to the temperature I'm ready to drink it at. So those are the 2 things we do, yes.
What are the buttons you press again to do the find intersection?
So, and this is the tool. So you want to look this calc function here right above the trace key. Anything in blue, I've got to hit the blue button is the way I think of it. So I go second calc, then I get this menu, and you could just enter number 5, or you can arrow down to it. I like to enter down because it looks like, you see what I'm doing. And then just hit enter, and then it's going to ask these, because otherwise you just sit there and you wait. Or I've had students, because it does give you a point, you think that's the point of intersection. Well, not quite. So first curve is a question, hit enter. Second curve is a question, hit enter. It's on the second curve. For your guess, hit enter, and you get the exact values. Okay. So be careful. I got some students who will do this, but then they trace to it, and you can't, but if you need the exact answer, you need to use these tools. The minimum and maximum tools will work the same. We'll be using those in a little bit as well. And again, you'll see if you go second calc, there's a lot of good tools here. There's minimum and maximum. There's zeros where it crosses the x-axis if we need that. We could also find particular values. This we could, evaluate, say at 15. We could have just used that tool, and then we enter 15, and it will jump when x is 15, there's y. So from the graph itself, you can do both evaluate and solve. Thursday, we'll look at ways to kind of do it with algebra, with using logarithms. We could also solve these. It's a little bit more cumbersome, but it's good to have more than one way. So if you've got this way of using the calculator, you will actually be able to solve every equation for the rest of class. And you actually go back anytime they ask you to solve, if you graph the left, graph the right, where they intersect, that's going to be your intersection. That's going to be your solution. Okay, so that get into trig, same thing. Okay, but use the graphing calculator. It's going to empower you because, again, it shows the whole picture of what's going on, not just one solution, but where multiple solutions might be. All right. And that's the end of that one. Let me, what time are we? We've got a couple minutes. How about if I take a quick peek at our homework, and let's just make sure we're ready to get through it. And again, what you should find is if you can at least start into each homework, get through a good portion of it by the next class, staying on track. And I know you've got different schedules. Maybe you do most of your homework on the weekend, but try to stay on track on a weekly basis. Then you're not all hit up with stuff as we get close to the test. Let's go to assignments. And we are now in 3.1, exponential functions. Let's see if this will let me. So yeah, we have about 16 questions. Two points on its graph. Let's jump here. There's some GeoGebra questions, but and again, what I do with the homework, as long as you can get to 70%, so maybe, you know, you can kind of pick and choose what you're working through a little bit, but make sure you get the overall gist. And as you come up with questions, go through it. So what's this one doing? 3x to the fifth, so it's a transformation. So a bunch of transformation type stuff. Let me jump down here to the end. We're given a model. How much will the house be? How much will a house now worth 60,000 be worth in 7 years? So you can use this function and your graphing calculator. Again, you're either going to evaluate or you're going to solve. So those last two things that we did should get you through there. We've got compounded interest, so there's a particular formula for compound interest. Let me give you that, so then you'll be able to handle this question. Compound interest formula. There's two of them. So with interest, they use the letter A for the accumulated value, so that's your balance at some particular time. You're going to deposit some money, that's called your principal. And compound interest is always 1 plus the interest rate divided by how many times it's getting compounded. It's probably in the book too if you want to look it up, but and then we raise it, and I'm going to put this in parentheses because you might need it. You raise it to the n times t, so where t is the number of years, n is the number of compounding. So if it's monthly, what would n be equal to? There's 12 months in a year. If it's daily, it's 365. And then R is your interest rate. There's another function so this is for periodic compounding, and that means by period. There's also one for continuous. And I'm not sure if we'll see that yet or not. I know it will come along. Continuous compounding is like, it's always happening. So a lot of times with population growth, they use this one. And that's the same thing. It's whatever you start with, which is your principal. And then we use the natural number. That's where the continuous compounding. And then it's your interest rate times t. Okay, so it's a simpler formula for continuous compounding. But those are the two different types. It's in the recording now. Maybe put it in your notes and we'll take a look. Again, since we have a little bit of extra time, if you have questions on them, we can probably start the next class with a few examples from here. But those are the two formulas you'll need. And notice they're exponential because the variable's up in the exponent. Okay. Questions? All right. So again, if you haven't done so far already, take a look, go into Canvas, into the grade book. You can see your grade for the exam, but more importantly, if you go in there, under the comments, I uploaded the scan of your test for the open answer ones and whichever choices you made. And again, if you want to take a look at the multiple choice, I'll have some of those with me after next class, and we could do that. All right. Thank you, and we'll get on to logarithms next class.